Okay, so what we did last time was Deuteron bound state, and we saw that this capital S has to be 1. You have two particles, S1 is equal to half and S2 is equal to half. So, they can combine to S is equal to 0 and 1, but then the measured total spin, total nuclear spin of deuteron is capital I is equal to 1, and that capital I equal to 1 can result from L is equal to 0, S is equal to 1, or L is equal to 2, S is equal to 1. It can also result from L is equal to 1 and then S is equal to 1 or 0, but since parity is positive and that is an experimentally measured quantity. So, L equal to 1 we do not consider, and with L equal to 0 you can have S is equal to 1 to get this plus 1, and for L equal to 2 also you need S equal to 1 to get I is equal to 1, and therefore, deuteron bound state is capital S equal to 1 state. So, first conclusion from this was that nuclear force is spin dependent, because in general if it does not depend on spin, then you should have both kinds of coupling, S equal to 0, capital S equal to 0 and capital S equal to 1. Since here it is all the time S equal to 1, so that tells that it is spin dependent, and then the spin dependent part, one suggestion was that include a term which is which contains this S2 S1 dot S2, right, because if you evaluate this S1 dot S2, which is S square minus S1 square and minus S2 square by 2, if you evaluate this, these things are fixed, these things are definite, and so for S is equal to 1 and S equal to 0 they will be different. So, if you put S is equal to 1, what happens? It is 2 h cross square and minus this is 3 by 4 h cross square and minus that is 3 by 4 h cross square and divided by 2. So, how much this was? This is for S equal to 1, and for S is equal to 0, if I put this part 0, then it is minus 3 by 4 h cross square. Okay. So, if I include this type of term in the Hamiltonian, then I have different interaction potential for capital S is equal to 1 and capital S equal to 0. People try to shift it equally both sides. So, they write some operator which is say half of 1 plus 4 by h cross square S1 dot S2. Okay. If you evaluate this for capital S equal to 1 and capital S equal to 0, it shifts equally. If capital S equal to 1, then this part is h cross square by 4, right. For capital S is equal to 1, this you can call it P sigma. So, P sigma will be half and then 1 plus, and this is h cross square by 4. So, this is another 1. So, half into 2, that is 1, and if you take S is equal to 0, it is minus 3 by 4 h cross square. So, this is minus 3. So, 1 minus 3 is minus 2 and divided by 2 is minus 1. So, this will give you minus 1. Right. So, if you have an overall thing and you want to shift because of this spin dependence up and down by equal amount, this is the right kind of thing to do. So, and then you also know this, this polyspin operator. Sigma S is written as h cross by 2 times sigma, just a scale change, right. So, if you do that, this becomes 4 by h cross square. So, 2 by h cross you put here, 2 by h cross you put here, and therefore, this P sigma is in terms of this operator, polyspin operators, they are called 1 plus sigma 1 dot sigma 2. Okay. So, in the potential, you to include this, you have that spin independent potential, and on top of that you add this. So, this is some R dependence and then this P sigma. Okay. So, this type of one has to work out what is this radial function here, which will give me right amount of mixing of this spin dependent and spin independent parts. Fine. Next thing we started discussion on was magnetic moments. Okay. So, magnetic moments are related to angular momentum right. For a classical particle going in a circle or a spherical charge distribution rotating about the axis, or a disk, charged disk rotating about axis, any kind of variation you take, a classical motion of electron or a charged particle or a charge distribution, the angular momentum and this magnetic moment are related. Mu z is equal to q by 2m times Lz. For if it is electron, for electron this thing will be mu z equal to E by 2me, Lz with a minus sign, negative charge, q is minus E, negative charge. So, and so this you write as minus h, you can put h cross here and h cross here, and then this becomes Bohr magneton mu b over h cross times Lz, right. Bohr magneton is E h cross over twice m e. Similarly, you define nuclear magneton, which is E h cross divided by 2 m p. So, if you have a proton which is going, which is moving, and it has got its angular momentum and its magnetic moment, they are also related by this. So, if you have proton and you are considering just this motion, then the corresponding mu z will be, or you can write it mu L z. Mu L z will be minus mu n, not minus, plus mu n over h cross times L p z. So, the relation between orbital angular momentum and the corresponding magnetic moment is same as in classical motion. But if you look at spin dependent part, magnetic moment corresponding to spin angular momentum. Okay. So, for electron you have mu electron, for electron you have this magnetic moment z component corresponding to spin part. This is okay. So, this is 2 times this, right, is 2 times, in fact 2.0023 times mu b by h cross and s z. Now, this 2 times, or it can be derived from Dirac equation. You, for electron you write relativistic quantum mechanics equation instead of Schrodinger equation, you write Dirac equation taking care of the relativistic effects, and from there one can really derive that the magnetic moment and this spin angular momentum should be connected in this fashion, and the factor comes out to be 2. And the measured factor is 2.0023, quite close. In fact, in Dirac equation also, if you take higher order correction terms, you really reproduce this. So, we understand why it is 2.0023. Using quantum mechanics, we understand that. Now, proton, you can just think that okay, the spin of proton is also half, spin of electron is half, spin of proton is also half. So, the spin part will follow this kind of rule. Instead of this minus thing, it will be plus thing, and that is all, right. But that does not happen, that really does not happen. If you write this as G, if you write mu z corresponding to spin, right. So, mu s z is equal to G times mu n over h cross and times s z. So, if you write this type of equation, what is the value for G? So, if it is proton, if you are talking of proton spin angular momentum z component here and proton magnetic moment here connected to this angular momentum, then this G factor turns out to be how much? 5.585691. These many decimal places are there because we know it to this accuracy, right. It is only the difference is in the last significant digit. So, Gs is this much, very different from what it is for electron, and that is because electron is a structureless particle, right. Electron does not have any internal structure. So, electron is just an electron and with no further inner structure, it is not a composite particle, it is a fundamental particle. Whereas, proton is not a fundamental particle in that sense, it has got internal structure. Inside proton, what it is? Proton is made of, I told you, 3 particles. What are they called? Quarks. Okay, UUD, up quark, down quark, and these quarks are confined inside that because of the strong interaction, and then that strong interaction is described in quantum mechanics or in particle physics in terms of what we call gluons. The exchange particle for this strong interaction between the quarks are gluons. So, in proton you actually have all these quarks and that gluons which keep them bound. So, it has got a structure inside. The charge is not just one single charge like electron, charge is distributed 2 by 3 e here, 2 by 3 e here and minus 1 by 3 e here, 2 by 3, 2 by 3 and minus 1 by 3. So, these charges are there inside and they have their own distribution inside, and the magnetic moment is governed by all that distribution. So, that is why it is so different from electron G factor. And for neutron also you have this magnetic moment. In general, you would think that neutron is a chargeless particle. There is no charge, therefore, there should be no magnetic moment. But then once again, neutron does not have a charge as a whole, but there is a charge distribution inside the neutron. Neutron is also made of quarks, and quarks are charged particles. So, you have UDD 2 by 3 e, minus 1 by 3 e and minus 1 by 3 e, making it 0. So, although neutron as such is a neutral particle, but it is not that there is no charge. The charges are there, positive charges are there, negative charges are there. So, they will have their own magnetic moments, and there will be a resultant magnetic moment, and that Gs, this is for GSP you can call it, and this is GSN, that is how much? Minus 3.826084. Okay. So, when you write this mu z taking contribution from the orbital angular momentum and spin angular momentum of proton, the spin angular momentum of neutron, you will write this as, let me write it GL. This is for orbital angular momentum, mu n over h cross and then Lz. This is the part coming from orbital angular momentum, and then you have Gs p proton and mu n over h cross times S p z, Sz of proton, P is for proton. So, Sz of proton, and this is the G factor for proton, and then neutron plus G n G s, let me write S n. So, S factor for neutron, and this is nuclear magneton divided by H cross S n z. Okay. So, this is the operator for magnetic moment z component. Now, if the nucleus has wave function, some wave function psi, we are talking of deuteron and its bound state. So, it is the wave function is the eigen function of that Hamiltonian with lowest energy. For deuteron, it is only one energy, one single bound state. So, if the wave function is psi, then what you have, this wave function psi depends on whatever quantities. This is for deuteron bound state, is an eigen function of Hamiltonian, right. So, an eigen function of Hamiltonian need not be an eigen function of this mu z. Okay. And therefore, the value of mu z in that bound state, if we calculate, that need not be a fixed definite quantity. If the wave function is not an eigen function of mu z, then mu z can have different values, mixed values. So, when you make a measurement, what you measure is the average value of this quantity. Mu z can have, say, these 2, 3, 5 values. So, if I make the measurement, there is some probability of getting that, some probability of getting that, some probability of getting that, and so on, if it is not itself an eigen function of mu z. But when we are making a measurement, we are not making measurement on one single nucleus. Any measurement will involve a stream of nuclei and all that. So, what you get finally is the expectation value or average value of this quantity in this wave function. All right. So, what the observed value will correspond to psi mu z psi. Okay. This is the expectation value or average value. Now, when you do an experiment, normally for measuring this magnetic moment, you apply some kind of magnetic field or so. So, this mu z get oriented. The magnetic moment, if you apply a magnetic field, the magnetic moment will turn and will take that direction of magnetic field, right. So, the z component of magnetic moment will take its maximum value. If you think in terms of classical mechanics, it's simple, you apply a magnetic field and then the magnetic moment will orient along that. So, if you ask what is mu z will be the value of mu itself, right, because the entire mu is in z direction. So, let me frame a sentence for it, which I can take to quantum mechanics also. Mu z has taken its maximum possible value, right. If the system is oriented, so that the magnetic moment has become in the direction of applied magnetic field, which I am calling z axis, then the z component of magnetic moment, which in this classical language equal to the magnitude of the moment itself, because now everything is in z direction. So, z component same as the magnitude. So, that is the maximum value. Now, this sentence is correct in quantum mechanics also. Whatever is the maximum possible value of that z component, that will be there, and that will correspond to maximum value of the orbital angular momentum z component. Okay. So, for deuteron I is equal to 1. What is I? Yes, this is the total angular momentum. So, total angular momentum that is I is equal to 1, its z component, right? Total angular momentum z component. So, these z components can be h cross 0 or minus h cross. If I is equal to 1, that angular momentum quantum number is 1, then you have these 3 possible values. This corresponds to m I equal to 1, this corresponds to m I equal to 0, and this corresponds to m I is equal to minus 1. If I is 1, m I can be 1, 0 or minus 1. So, the maximum value of m I is 1, which is same as I. So, m I equal to I, that gives you the maximum value of m I. So, the observed value corresponds to the situation where m I is the total angular momentum and other things are also there, and m I should be equal to I. This wave function I should use if I want to compare the observed value, experimentally observed value, with calculated value, calculations. So, I should make calculations with this wave function. Same. In case of deuteron, assuming central potential, assuming that L is equal to 0, orbital angular momentum part is 0. So, one thing is this part we will make 0, because the orbital angular momentum 0, this part will 0, and the other thing is that this wave function I m I is equal to I, that wave function corresponds to s is equal to 1, because I is L plus s. So, s is 1, I is 1, s is 1, with 0 I can combine, s is 1, and if s is 1, that means when I say m I is equal to 1, that means s z is equal to 1, and that will happen when s 1 z is half and s 2 z is half h cross, right. This is this state, both spin up. S is coming from S 1 plus S 2, and therefore, S z is S 1 z plus S 2 z. So, if you need this capital S z equal to 1, you need both of them plus half, only then this will be 1, right. So, spin up S 1 z is h cross by 2, S 2 z is h cross by 2, and this state is this wave function is given by both spin up. So, let us now try to calculate this mu z. This mu z is, I am trying to calculate this quantity mu z. Let me write it this way, mu z equal to, this part is 0, first part, Lz part, here it is GSP. So, it is this wave function, then GSP mu n over h cross, these are constant numbers, and then SPZ, proton, z component, spin. So, that is 1, okay, and then plus GSN mu n over h cross SNZ, right, and then the wave function. So, two parts, one part is GSP mu n over h cross SPZ, and the second part is GSN mu n over h cross and S n z. Okay, just written the two terms separately. Now, the first term SPZ. SPZ is an operator operating on this. The first arrow is for proton, second arrow is for neutron. So, SPZ, this operator will only operate on proton, and this is a spin up. It is an eigenfunction of this operator with eigenvalue plus h cross by 2. So, this operating on this wave function will give me h cross by 2 into this wave function, right, because here the z component of spin of proton is definite, it is h cross by 2. So, this is an eigenfunction of SPZ. So, when you apply this SPZ on this, it will just give you that eigenvalue times the function. So, this quantity is GSP mu n over h cross, and I am calculating this, this gives me h cross by 2 times this. So, it is spin up here and spin down spin up here. All right, SPZ is already operated on this, and it gives me h cross by 2, which I have written here, times this wave function, that wave function is written here. And since this is normalized wave function, this quantity is 1. And similarly here SNZ, this is neutron spin z component. So, and here you have proton spin up and neutron spin up. So, it will operate on neutron part, proton part will just remain as it is, and neutron part spin is definite, z component of spin is definite, it is up. So, it is h cross by 2. So, when this operate on this, it will again give you h cross by 2 into the same wave function. So, this is GSN mu n over h cross, then h cross by 2, and then this same wave function. Okay. So, that is mu n over 2, this h cross cancels, and mu n over 2 I can write here. So, mu n by 2 I have written, it is GSP, and this quantity is 1 plus GSN. It is GSP and plus GSN. Now, put the values, mu n by 2, GSP is written here and GSN is written here. So, tell me how much it is, GSP plus GSN, 1.759607. So, divide by 2, 0.879835. Okay, let us keep it up to here, times mu into it times nuclear magneton. So, if I assume that the nuclear potential between proton and neutron is a central potential, and the ground state of deuteron corresponds to L equal to 0, which it will be if it is a central potential. So, the bound state of deuteron corresponds to L equal to 0, and then use that fact that the measured total spin capital I is 1. That is all. I am not using 36 MeV and this and that. The detailed structure of potential I am not using. Potential is central, that assumption we have taken, right. Then with that central potential, L equal to 0 will give you the minimum energy state. Deuteron bound state is the minimum energy state, in fact, the only bound state is no excited state, and measured value of capital I is 1, therefore, capital S is 1, and with capital S is equal to 1, how the wave function will operate on this mu z. So, without going into the detailed structure of that nuclear potential, I can make this calculation that magnetic moment z component should be equal to this. Now, compare with what people have actually measured. So, this is the thing which is coming from the central potential thing. Now, the measured value, experimental values is 0.8574 mu 1. Right. So, the agreement is there, but not very good. The kind of accuracies that we obtain from experiments, for that a difference in the second significant digit itself, 8574 here, 8798 here, is not insignificant. We cannot say that okay, good, very good agreement. It is not very good, although the order of magnitude is correct. So, we are on the right track, right. The kind of discussions we are doing is not very off the reality, but then the difference must be addressed. The difference is large enough to draw our attention that the things are okay, but not very good, not very perfect. So, what are where are we making assumptions, and where we have to modify our assumptions? All other things that I am doing on the board, they are all standard things. The G value of proton and G value of neutron are known to very high accuracies. That is why we are putting so many digits there. Yes. Then mu z depends on Lz, Spz, Snz, that is standard, well known. The calculations are all perfect. In the calculations we are not using detailed wave functions, okay. Detailed wave functions we are not using. So, the only thing where we are making some assumptions which needs attention is we are using the fact that the nuclear interaction potential between proton and neutron is central potential, because only then L is equal to 0 will come. The lowest energy state corresponds to L equal to 0, that comes from this assumption. That is the only thing we are doing. So, we have to modify that assumption. This slight discrepancy between the measured magnetic moment of deuteron and the calculated magnetic moment of deuteron, that tells me that nuclear force is not entirely central. It is close to central, but you should add some part, to this central potential, which allows you for another L value, and that another L value can only be L equal to 2, because that capital I equal to 1 is sitting on us. Capital I equal to 1 is a measured quantity, so that we have to honor, right. Anything coming from experiment we have to honor, we can only modify our theory. Experimental result is experimental result. If the experiment has been done carefully and if the experiment is repeated several times at several places, all the time you find that okay, this is the value, that has to be taken, that is there. Theories you have to modify. So, capital I equal to 1 will tell me that only L equal to 0 or L equal to 2 can be brought in. If I only bring L equal to 2, what happens? First thing is, why L equal to 2? L equal to 0 will give me the lowest ground state, and pure L by 2, L equal to 2 will be much higher energy. Whatever potential you take, if it is largely central potential, then L equal to 2 cannot be alone there. So, there is a mixture of L equal to 0 and L equal to 2, and this nearly good agreement tells that L equal to 0 part will be dominant. So, it is largely L equal to 0 state, some part of L equal to 2 state should be there. This L equal to 0 and L equal to 2 having simultaneous existence in that wave function, that can only happen if you add some non-central part, some tensor part in the potential, then only you can have this mixing. Now, so the message from this slight disagreement is that you must add some kind of non-central part in the nuclear potential. Nuclear interactions are non-central, right, are non-central. So, how much of L equal to 2 should go into it, right? How much of L equal to 0? If there is a mixture, if the wave function, ground state wave function of deuteron corresponds to simultaneous existence of two angular momenta, orbital angular momenta, L equal to 0 and L equal to 2. So, how much of L equal to 0 and how much of L equal to 2 will give me this value, measured value. So, that one can do. If you make a calculation, I had made this calculation for L equal to 0. Now, you can also make a calculation for L is equal to 2. So, if you do that, L is equal to 2. Now, if L is equal to 2, and remember I must be 1 and S is equal to 1, these combine to I equal to 1, right, and I is L plus S. So, I z is L z plus S z. What I need is M I equal to I. So, the total I z, I need this, I need 1 M I I need equal to 1, and L z and S z, correct. You can write in terms of M, or otherwise H cross will come everywhere. So, this is M L and this is M S. So, M L plus M S should be 1. Okay. So, we will just see what values of M L and what values of M S can give me 1. Okay. We will just do that. So, since L is equal to 2, M L can take values 2, 1, 0, minus 1, minus 2, and S is equal to 1. So, M S can take values 1, 0 and minus 1, and M L plus M S should become 1. So, what combinations are allowed? You can see one combination is this 2 combines with this minus 1, M L is equal to 2 and M S is equal to minus 1. This will give you M L plus M S equal to plus 1. What else? This M L is equal to 1 and M S is equal to 0. This will give you M L plus M S equal to 1. What else? This one and this one, M L is equal to 0 and M S is equal to 1. Anything else? So, there are 3 different possibilities of making this M I is equal to I. Correspondingly, if I write the in symbols, M L equal to 2 and L is equal to 2. So, that angular part will be y 2 theta phi, L is equal to 2 y L M theta phi part. So, that 2 will be here, M L equal to 2. So, that 2 is here. With it goes M S is equal to minus 1, and remember M S is the proton M S and plus neutron M S, that is the total S. Total S is equal to 1. It is coming from S 1 plus S 2. So, minus 1 will mean that you have this wave function. Spin part is like this. Proton spin is minus half, Z component. Neutron spin is minus half. So, that this M S is minus 1. So, that is this first one. Second one is more complicated. M L is equal to 1. So, y 2 1. So, L is 2 and M L is 1. So, that will give you y 2 1. M S equal to 0. M S equal to 0, what do I write? 1 up and 1 down. Why not the first one down and second one up? This is capital S equal to 1. So, capital S equal to 1 corresponds to ms equal to minus 1, ms is equal to 0 and ms equal to 1. In terms of that individual spins, this corresponds to down down, this corresponds to up up, and this corresponds to, this will correspond to 1 by root 2 up down plus down up, right. So, it is 1 by root 2 and then up down plus down up. This will be the wave function, right. And the third one, you can work out with the third one, simple. This is ml equal to 0. So, you should write y to 0 here and ms is equal to plus 1, that is up up. Okay. Now, what I had already calculated earlier with L equal to 0 was L is equal to 0, ml is equal to 0 and this up and this up. With this wave function, I had calculated this mu. Okay. This operating on L part will give you 0. So, this term goes out and then in other calculations this up up is the wave function which will be operated by these things. So, they will give some values, I have done that. Now, similarly, this time you have to keep this Lz and operate, start with this y22 down down and operate this operator mu z on this wave function. So, Lz will operate on this and similarly that Spz and Snz they will operate on this. So, do it for this, do it for this, do it for this, right. You can do that just like I had done starting with this function. I have calculated this average of mu z. Similarly, starting with this wave function or this wave function or this wave function, you can find that. Now, the wave function which we call I is equal to 1 and mi is equal to 1 and of course, L is equal to 2 and S is equal to 1. This is a wave function we are trying to construct and we see that there are 3 terms available, this one, this one, this one, all 3 correspond to this, right. All these 3, where are they coming from? Where did I write them from? I wrote from here. And where did I write these from? These were written to make that capital I equal to 1, which combinations will make capital I equal to 1. So, the wave function capital I equal to 1, capital mi is equal to 1, I is equal to 1, mi is equal to 1 with L equal to 2 and S equal to 1 will have all these 3 combinations. Okay. So, that comes under how you couple these 2 angular momenta, Klebsch coordinate coefficients and all that, and it turns out that you have 3 by 5 times this first one y22 down down plus root 3 by 10 of this second one y21 and then that spin part, and this is 1 by 10 and then this y20 part. This is the wave function. So, you actually have to work with this, okay. But separately if you have worked this mu z average with this wave function and gotten some value, then this wave function gotten some value, this wave function gotten some value, then you can, using those 3 you can calculate the net mu z. That will be this square into value corresponding to this, plus this square into value corresponding to this, plus this square into value corresponding to this, and see these coefficients are squares of them should add to 1. So, this will be 3 by 5, that is 6 by 10, plus 3 by 10 is 9 by 10, and plus 1 by 10 is 1. Okay. So, do all those calculations and start with this wave function, use this wave function to calculate average value of mu z, multiply by 3 by 5. Then use this wave function to calculate average of mu z and multiply by 3 by 10. Then use this wave function and calculate, and then you multiply by 1 by 10 and add all those things. You will get expectation value of mu z in this wave function, this full wave function. When you do that, you can do that, okay? This your homework, that mu z corresponding to L is equal to 2, that part turns out to be 0.3101 mu n, and mu z average with L is equal to 0, that we had already done, 0.8798 mu n, and the observed value is 0.8574 mu n. From this we can work out how much of it is L equal to 0 and how much of it is L equal to 2. So, if I write the wave function as A times say L is equal to 0 plus B times L equal to 2, right, a mixture of two L values, L equal to 0 and L equal to 2, only these two are allowed because capital I is 1, remember. Then the value of mu z should be mod A square, value coming from here, that is 0.8798 mu n, and plus mod B square, value coming from here, it is 0.3101 mu n, and observed value, this is the observed value, in this side this is this, it should be this, and if this corresponds to observed value, so this is also equal to 0.8574 mu n. So, you have a relation between A square and B square, and the other relation is A square plus B square should be 1. If I am writing wave function in this fashion, it has to be normalized, and these two are separately normalized. So, A square plus B square should be 1. So, with these two you can calculate how much is A square and how much is B square. When you do that, you find that this A square is 0.96 almost, and B square is 0.04. So, the magnetic moment, observed magnetic moment suggests that the ground state wave function of deuteron corresponds to two orbital angular momentum quantum number existing simultaneously, L equal to 0 and L equal to 2. L equal to 0 is 96% and a 4% admixture of L equal to 2. So, the small non-central part has to be there. 96% is still this. Now, this similar conclusion can be drawn from what we call electric quadrupole moment. You know that electric quadrupole moment of a charge distribution. If you have a charge distribution, there is some charge in some volume, some charge distribution given by rho r. Rho is the charge density, charge per unit volume. You can write its monopole moment, then dipole moment, then quadrupole moment, octopole moment, and so on. Monopole moment is just the total charge contained here. Then dipole moment, you know, this r vector times, right, you take some origin somewhere, then dipole moment will be r vectors times rho d tau integration. Similarly, you have quadrupole moment, and in quadrupole moment we define is as q I j. I will just explain what are I j, and E times, let me write E times q I j is rho, which is a function of r, and then 3 x I x j and minus r square delta I j d tau. What is this d tau? D tau is a small volume element in this distribution. So, take some small volume here and call it d tau. This is d tau, and where I have taken that, that is this r vector, that is this r vector, and at this position given by this r vector where I am constructing d tau, the charge density is rho at r. This rho r written here is the charge per unit volume, charge density at this point. So, multiply this rho by d tau gives you the charge contained in this volume, in this small volume, right. So, that is rho and d tau. Now, come to x I x j. So, x I x j, x 1 means x, x 2 means y, and x 3 means z. So, these are coordinates x I x j, x I x j are coordinates of which point? Coordinates of this point where you are constructing d tau. So, x I x j, and r is distance from origin to that volume element, that is r. So, this is it. So, you can write for example, E q x x, that means I am putting 1 and j I am putting 1. So, q 1 1, q 1 1 is same as q x x. This is rho r, and then you have 3 x 1 is x and j is also 1. So, x 1 is x. So, this is 3 x square, and this is delta I j, this you know, Kronecker delta, this is 1 if I equal to j and 0 otherwise. So, here if I am putting 1 1, I equal to 1, j equal to 1, this is 1. So, minus r square d tau. So, d tau is constructed at the point given by coordinates x comma y comma z, and this is that x, and r is the distance from the origin, and rho is at that point, charge density at that point. Similarly, you can write E q x y. E q x y will be rho r, and then 3. So, 1 2 I am putting 1 2. So, it is 1 2 x y d tau. This part is 0, and similarly you can write everything. Generally, in an experiment we measure q z z. Okay, we measure q z z. E q z z will be rho r, then 3 z square and minus r square d tau. You will have 9 of them, x x, x y, x z and so on, you will 9 of them. Experimentally, we generally measure this one. Okay. Now, the first observation is, if the charge is spherically symmetric, if the charge distribution is spherically symmetric, that means charge density at position vector r is not a function of theta phi, it is only a function of r. Same distance you go in any direction, so you will construct a spherical surface, the charge density is same everywhere on that spherical surface. we call it spherically symmetric charge distribution. Like a uniformly charged sphere is a spherically symmetric charge sphere distribution, or it may depend on the distance r. So, you may have this layer is more dense and this layer is less dense and so on, but then on that spherical surface it should not depend on theta phi, not that on this side you have more charge and on this side you have less charge. Okay. So, if it is spherically symmetric, you work out that this quadrupole moment will be 0. For example, look at QZZ, it is 3 z square minus r square, then rho at r d tau. Okay. So, if you look at this z square rho d tau, that should be equal to y square rho d tau, and that should be equal to x square rho d tau, correct? Because it is spherically symmetric, this x axis, y axis, z axis, they are all equivalent. So, x square into rho d tau, y square into rho d tau, z square, they are all same, and therefore, and if you add these three, you will get x square plus y square plus z square, that is r square d tau. So, each of them should be 1/3 of r square rho d tau. So, you can see here 3 times z square rho d tau and r square times rho d tau, they are equal, because each of them is 1/3 of r square rho d tau. So, 3 times of that it will become equal and it will be 0. So, if you have a spherically symmetric charge distribution, the quadrupole moment, electric quadrupole moment is 0. Okay. Now, Deuteron, if it is a purely central potential and the wave function corresponds only to L equal to 0, if that is spherically symmetric, that wave function is spherically symmetric, does not depend on theta phi, does it? L equal to 0, y 0 0 does not depend on theta phi, is a constant. Spherical harmonic, capital Y 0 here, 0 at the top, that is just a constant, square root of 1 by 4 pi, does not depend on theta phi, and theta phi dependence is coming from here only. So, if it is a pure L equal to 0 state, its a wave function, and hence that charge distribution, probability of finding the charge here and there and there and there, is spherically symmetric. And if this is spherically symmetric, it should correspond to q equal to 0, right, qzz equal to 0. We measure only qzz, that is why I am writing this. Whereas, the observed value of qzz for Deuteron bound state is 2.88 into 10 to the power minus 27 centimeter square. It is small, but still it is there. The unit of quadrupole moment QZZ is area, you can see from the definition. I have put this charge E here. So, rho d tau is charge. So, rho d tau is charge and this E is here, that is charge. So, this Q in itself is just this part. So, length square area. So, Q value of Q will be in area units. So, centimeter square. So, this is the observed value, it is not 0, it is small, but not 0. So, this small value, but non-zero value tells me that your wave function of Deuteron is not purely L equal to 0. If it is purely L equal to 0, it should have been 0. So, if it is not purely L equal to 0, you have to bring in L equal to 2 together with L equal to 0, and again the same sequence of arguments. If L equal to 0 and L equal to 2 are both present in the ground state wave function, then the potential cannot be purely central. So, you have to bring in some non-central part. And here also, if one calculates the wave function for L equal to 2 and makes a calculation that how much mixture will give me this value, how much mixture of, in what proportion I should mix equal to 0 wave function and equal to 2 wave function to get this. If you do that, it comes out to be almost the same. That value that I had written, that if you write psi as A times L equal to 0 part plus B times L equal to 2 part, then mod A square is 96% 0.96 and mod B square is 0.04. That also gives me this. It gives me the right kind of magnetic moment 0.8574 mu1, and this same proportion of mixing also gives me right kind of quadrupole moment. So, this tells me that you have some kind of non-central part in the potential, right. We will stop here.